Hello and welcome to the next what the heck video. So this is going to be a video where I graph all of the inverse hyperbolic functions in this video. I'm going to graph all 6 of them. I'm going to show you how we get to them. We're only going to need a couple of domain restrictions, unlike having to do a domain restriction for all of the trigonometric functions. The only 2 that are going to require a domain restriction are the cosine and the hyperbolic cosine and the reciprocal of that, the hyperbolic secant. That's really all I have to say about what's going to happen in this video. After this, I'm going to do a video where I show the logarithmic version of a few of the inverse trig functions, as well as a few of the inverse hyperbolic trig functions. And then after that, I'm going to do a little video on a very, very interesting constant, which has to do with a completely different conic section, but can still be represented in terms of one of the functions that we're going to derive in its logarithmic form. And then after that, I'm going to do a video where I explore the analogous relationships with the geometric representations of all the hyperbolic functions using the unit hyperbola instead of the trig functions and the unit circle. And that's going to be the next few things, and then after that I'm probably going to start delving more into Euler oily macaroni again, and we'll see where we go from there. I have a lot of things that I want to do, so it's sort of just throwing things around until I've made them all, right? But I'll get to everything eventually, and I'm sure there's more on Euler's formula to come as well. It just depends on when I get to it, and when I finish Dr. Euler's Fabulous Formula, that book. But since I've been back from Barbados, I've actually finished an entire book over that vacation. I read Alex Bellos's Alex's Adventures in Wonderland, which was just an absolutely delightful book. It covered so many interesting topics. It got wet a couple of times, so it's not in the best shape. You can't really tell from the camera, but it's I read through it in a week. It's like 450 pages, I think, something like that, 420 something pages, but you know, I never thought, you know, a year ago I'd be reading an entire book in a week that's this long, you know, 450 pages. It took me a year to read Christopher Hitchens's memoir, but that was sort of the, whatever, the getting the ball rolling, right? And now I can't really stop reading. I love it now. It's strange. I never thought I would do it as much as I am. But I read this over the weekend, over the week, when I was in Barbados, and I've read through quite a bit of Matt Parker's Things to Make and Do in the Fourth Dimension. It's a delightful little book. I haven't made any of the things in it. I don't really plan on it, but I'm looking forward to finishing it. Other than that, I still have to finish reading Dr. Euler's Fabulous Formula. Interestingly enough, a book to follow up the book on the constant E would be, not ironically, but interestingly, a book without any E's in it. So this has nothing to do with math, it's just a fictional story, but it's called Gadsby, a story of over 50,000 words without using the letter E. So this will be my cure to way too much about E. It'll be interesting. That means it doesn't have the word the in it. No THE. I just want to, again, personally thank Flammable Maths for allowing me to be on his channel in his Complex Numbers But Different series. Very, very good series. I recommend everybody watches it if they can. Let's get to the video at hand. Okay, so as I said in the intro, we're going through the graphs of all of the inverse hyperbolic trig functions, sometimes called hyperbolic trigonometric functions, even though they're not really having to do anything with triangles. They're simply called that because they're nice analogies of the regular circle trig functions to the hyperbolic trig, you know, to the hyperbola. Instead of the unit circle, it's the unit hyperbola. But these are going to be the inverse functions, and so I'm going to draw the axes, the xy axes, so x and y. So the inverse hyperbolic sine is simply going to be a reversal of the hyperbolic sine function over the line y equals x. So first I will draw it in dotted green, and if we recall from the last video, it grows and descends quite quickly, exponentially in fact. It's probably pretty hard to see, but when I draw it in solid green, you'll be able to see it. And all we're simply going to do is flip it over the line y equals x. You'll notice that since it's an odd function and it is 1 to 1, it does not fail the horizontal line test, which means we don't have to do any sort of domain restrictions here, right? Every value that the function hits, it only hits it once, so it won't, its inverse will be perfectly well defined over the entire domain. So all we have to do is reflect it over the y-axis, over the line y equals x, and we end up with this interesting function, which will grow logarithmically down in the negative direction and up in the positive direction. And it's perfectly well defined everywhere. It has, just like the hyperbolic sine function, and it's not really any different except that it's reflected over the line y equals x. So it is an odd function. It is rotationally symmetric about the origin, much just exactly like the hyperbolic sine is. So this is the inverse hyperbolic sine, so SINH inverse of x, right? And the hyperbolic cosine is actually one of the two functions that we need to do a domain restriction on, because if you recall, the hyperbolic cosine is an even function, and all even functions have not so well defined inverses because they hit values more than once. In multiple points in their domain map to the same point in their range. So we have to restrict the domain, and the most natural restriction to make is to simply do x greater than or equal to 0. That way we consider the positive branch, which is simply just the common way of doing it. And since we know that the hyperbolic cosine is always more than the sine, the hyperbolic sine, we know that its inverse, when we reflect it over the line y equals x, it's going to always be less than the inverse hyperbolic sine. So it will start here, and we know that at 0, the hyperbolic cosine is 1, so at 1, the inverse hyperbolic cosine is 0. Right? And it will sort of get closer and closer to the inverse hyperbolic sine by approaching it from underneath, and much like the hyperbolic sine and hyperbolic cosine approach each other in value, these will approach each other in value as well, and so this will simply just hug the inside like that, and that's the hyperbolic cosine. That's it. I'm sorry, that's the inverse hyperbolic cosine. It's as simple as that. So I'm going to erase the dotted representation. And that's simply those two graphs, right? We have one where we have to reflect it over the line y equals x, and we get a perfectly well-defined function all the way across. And then the other one, we had to restrict the domain because it's an even function, and so that's sort of required. So now that you've seen these two, we're going to move on to the inverses of the reciprocals of the hyperbolic sine and hyperbolic cosine, which are the inverses of the hyperbolic secant and the hyperbolic cosecant. So let's erase these. And now let's recall what the hyperbolic cosecant looks like, right? The hyperbolic sine goes through 0, right? And so if we're dividing 1 by 0, it's going to be undefined at that point. And so it's going to, we remember that the hyperbolic cosecant comes down from above and approaches 0 quite quickly. This is not the graph y1 over x, right? It's not the same thing, because and all we have to do is simply reflect it across y equals x, and we end up with the proper graph. But because it looks like this, it almost essentially looks the same, right? Very, very much approximates a hyperbola. But to be sure, this graph is not 1 over x. It's 2 divided by e to the x minus e to the negative x. That's this graph here. And so we're inverting that function. This is not 1 over x, right? So we're inverting that function, and it essentially looks the same almost, but it's going to look like... One thing to note is that it approaches its horizontal asymptote much quicker than it approaches its vertical asymptote. So that's sort of the visual difference that you should see, is that it gets closer to the x-axis much quicker than it gets closer to the y-axis. So when we invert it, we will see that it actually gets much closer to the y-axis quicker than it gets closer to the x-axis. So it will look something like this. Right? It will exchange on a point of y equals x, and it will do the same here, right? It will get closer to the y-axis much quicker than it gets closer to the x-axis, and so they will trade places like so. And so what I did was I reflected it across a point where it lies on y equals x, and it gets closer to the y-axis than it does the x-axis, which is the opposite of what the original function does. The original function gets closer to the x-axis than it does the y-axis, or more quickly, I should say. They get the same distance away because they both approach both asymptotically at different speeds, and so that is clear when you invert them. And so unfortunately, this function doesn't look much different than its actual regular, the inverse function doesn't look much different than the regular function. Many functions are their own inverses, for example, 1 over x or x, right? But unfortunately, this function is so close to its own inverse, but it's not actually the same as its inverse. But it is, in fact, an odd function, just like the hyperbolic cosecant, whereas this is the inverse hyperbolic cosecant. Unfortunately, it's rather boring. It doesn't look much different from how it normally does. Then there's the hyperbolic secant, which, if you recall, is this bell curve shaped thing, which is always less, or at least on the positive side, it's always less than the hyperbolic cosecant. But notice, it's again an even function, so when we invert it, we have to be sure to restrict the domain first. So again, we're going to do the usual convention of eliminating the negative inputs and only considering x to be greater than or equal to 0. And so the range goes from 0 to 1, and when we invert it, it will look like this. So I'm going to erase this, and I'm going to draw it here. It looks like that. So it's always less than the inverse hyperbolic cosecant, and this is the inverse hyperbolic secant. Rather mild looking, but of course if we continued the graph down here, we would see that it wouldn't be properly defined. So we did have to restrict the domain, and the hyperbolic cosine and hyperbolic secant are the only two that we have to restrict the domain of, because they're the only even functions. All the other functions are odd, and their inverses are perfectly well defined. So that's the inverse hyperbolic cosecant and the inverse hyperbolic secant for you. Now to move on to the last two, the inverse hyperbolic tangent and the inverse hyperbolic cotangent. So, I don't know why I just erased the axes, but here we go again. So this is the x-axis and this is the y-axis. Again, the hyperbolic tangent is the hyperbolic sine divided by the hyperbolic cosine. So it is 0, if we recall, it is 0 at 0, and it approaches 1 and negative 1 asymptotically, right? It looks like this, sort of, and approaches negative 1 from above and 1 from below. And so when we invert it, it's simply going to approach positive infinity as it gets closer to 1 and negative infinity as it gets closer to negative 1, because when we invert it, it's all going to point in the opposite direction, and so this is the graph we're going to end up with. Again, it looks rather like the tangent function, but it is not. It is simply not equal to that. If you expanded its domain out by a factor of pi over 2, you would see that it does not line up with the tangent function, even though they may have the same asymptotes if you do that. But it simply is not the same function. We've inverted the hyperbolic tangent, and now it has vertical asymptotes as opposed to horizontal ones. But because the domain's flipped, we know what these vertical asymptotes are. They are simply x equals 1 and x equals negative 1. Right? Now, since the hyperbolic cotangent is the reciprocal of the hyperbolic tangent, we know that the function that it was approached 1 from above, because the hyperbolic tangent approaches 1 from below, so the reciprocals start off infinitely large because it is 0 at 0, and then it approaches 1 from above, and it comes from negative infinity on the negative side of the y-axis and approaches negative 1 from below, just like the hyperbolic tangent approaches negative 1 from above, because they're reciprocals. And so when you invert them, we end up with a very similar looking shape that looks like this. And here we have our inverse hyperbolic cotangent. So the green one is the inverse hyperbolic tangent, and the red one is the inverse hyperbolic cotangent. Unfortunately, these are, again, rather boring looking functions. They don't look that interesting, they don't behave that interestingly, but because I want to start getting into the topic of hyperbolic functions a bit more, I figured I would cover all of them, just like I covered each of the regular trig and inverse trig functions. One thing to note, the inverse hyperbolic cotangent is a little weird, because how many functions do you know that have two vertical asymptotes, negative 1 and 1, and then have nothing in between, right? It seems a bit odd, it seems slightly weird. I think you'll find that these functions together sort of describe the same idea, but they represent different domains of that same idea. But more on that later when we go into the logarithmic forms of all of the, not all of them, but into the logarithmic forms of some of the inverse trig and some of the inverse hyperbolic functions. But that's been all 6 of the inverse hyperbolic functions graphed for you in all of their glory. So thank you very much for watching. In the next video, we'll be covering some of those logarithmic forms. So thank you very much for watching. Quick little thing, this channel has an Instagram, so it is at whatthehectagon, of course, and it has a Twitter also. So this is Instagram, and of course this is Twitter, and it is of course naturally Of course, naturally, of course, also what the hectagon, at what the hectagon. Nope, at the hectagon. Oh, can't spell today. Okay, hectagon. And my email is the incorrectly spelled what the hectagon. Why spell check before you make the email, right? That you can't then change, at gmail.com. Now, all of these are in the description if you don't want to have to somehow watch the video and pause it and actually write it down. Along with other Instagram, Twitter, YouTube accounts that me and my friend Bill run. He does one for D&D. We together stream on Mixer under the moniker of Fredwood Live. So check the description for other stuff. This is just for my channel. This is my Instagram, at whatthehectagon, Twitter, at whatthehectagon, and email, at whatthehectagon, because I spelled it wrong when I made the email and now I can't change it. So that's the stuff. Thank you for watching, and bye-bye.